Welcome to the session. Today we are going to talk about what is Carnot's reversible engine. Carnot's reversible engine. See, it is a device. Carnot's reversible engine is a device. Which converts heat energy into work. It is a device which converts heat energy into work. So let us see what are the components present in the Carnot's reversible engine. So here there are 4 elements in this engine. So now the first one is what we call this one, system or working substance. Here I am taking working substance which contain a cylinder with piston. Okay, which is filled by 1 gram mole gas. 1 gram mole gas. See, working substance. This is what we can say, working substance. Simply we can say system. It is a system. Understand? Now one more thing we have to take here is source, and then the next one is insulator, and the third one is sink. See, source, insulator and insulating stand, we can say that, and sink. Now the source which is maintained at high temperature, where the source is maintained at high temperature, so that temperature can be T1 degree Kelvin. The temperature of the source can be T1 degree Kelvin, and also it has high thermal capacity. Because we know that if the amount of heat is taken from the source or given to the source, there is no change occurred in the temperature of the source. So that is why I am taking the high thermal capacity, where the source has high thermal capacity. Where I am taking insulating stand, understand, you know very well. And one more thing is sink. So where the temperature of the sink is T2 degree Kelvin, which is equal to the temperature of the surrounding. It's simply we can say that cold body, where sink can be taken as a cold body, whose temperature is equal to the surroundings temperature. Okay, source, insulator, sink. Then the temperature of the source is very high. It has high thermal capacity, and where the temperature of the sink is equal to the temperature of the surroundings, and where we can take working substance. So these are the elements majorly present in the Carnot's reversible engine. It is a theoretical engine. Now, so our aim is, we are going to find out how much work is done during this process and what about the efficiency of this Carnot's engine. So let us see one by one. Initially, so we are going to find out what is work done in this process. See, let us see, in Carnot reversible engine, we have to put this concept in your mind. Working substance which contain 1 gram mole gas, source, insulating stand and sink. The temperature of the source is more than the temperature of the sink. That means what? T1 is greater than T2. Understand? So you have to put this concept in your mind. So let us find out how much work is done this process. Right. So work done. Work done in Carnot engine. In Carnot's engine. Or we can say work done in Carnot cycle. Work done in Carnot cycle. Understand? Here we are about to use PV diagram. You know that PV diagram, right? So PV diagram we are going to use here. Understand? PV diagram. So which contain 4 points A, B, C, D, and volume can be taken on the x-axis, and where we should take pressure on the y-axis. Understand? Now, so here in this case, here you have to remember that a point A can be taken as P1, V1, and the T1. P1, V1, T1. At point B, here we can take P2, V2, and the T1. So it's clear there is no change in temperature at points A and B, and at C we have to take T3, V3, T2, and here we have to take pressure has P4, V4, and the temperature remains same just like as point at C. Understand? So this is the PV diagram. With the help of this diagram, so we have to evaluate how much work is done during this process. So for this, here we are going to follow 4 steps, 4 stages we are going to see. First one is isothermal expansion. Isothermal expansion. And the second one is adiabatic expansion. And the third one is isothermal compression. And the fourth one is diabatic compression. Here we'll go through 4 stages. The first stage is what here? Isothermal expansion. And the second one is diabatic expansion. And the third one is isothermal compression. And the fourth one is diabatic compression. Understand? Right. See in the picture, the way A to B is what? It represents isothermal expansion. Isothermal expansion. Understand? Now, the way from B to C represents diabatic expansion. And the way from C to D represents isothermal compression. In shortly we can write IC. And the way from D to A can be taken as diabatic compression. So that can be written as where AD, diabatic compression. Understand? So these 4 stages, let us see one by one initially. Okay. So first one is isothermal expansion. See what happened in isothermal expansion actually. What happened in isothermal expansion actually? See there, initially, let us assume initially a system can be taken. You know that the system contained 1 gram mole gas with a piston, and now I'm taking the working substance and placing on the source, right? So we know that what I'm doing there, I'm putting working substance on source. Understand? You have an idea about that 4 elements: working substance, source, insulating stand and sink, right? So where the source is at high temperature, the temperature should be T1 degree Kelvin. Now what I am doing, I am putting that working substance on the source, right? Now I am allowed it to expand isothermally. What happens if it is expanded isothermally? We know that work done in the isothermal process, right? When it is expanded in isothermally, that means gas itself is doing work on against the surroundings, right? So when it is expanded slowly, what happens? After certain time, its temperature is come down. Understand? After certain time, its temperature is come down to compensate the temperature. Immediately, system can receive some heat from the source. We know that source has high thermal capacity. Now, where the working substance can receive some amount of heat energy to compensate, to balance, or to overcome the loss of temperature, right? Then after that, we know that the temperature of the working substance remains constant, that is at a T1 degree Kelvin, right? So in the process, how much work is done by the system, we have to find out that value. Understand? Now, the work done by the system, we know that very well. The formula can be written as W is equal integral PdV. See there, from that's isothermal expansion line. You have to observe here, isothermal expansion line from A to B, where pressure and value both are variables and the temperature remains constant. Understand? So, but here, just let us consider that pressure is also constant. Right. So let us take this formula W equal, that is what done by the system can be W equal integral PdV. Right. So now, what about the volume? Volume can be changed from V1 to V2. Then you have to write V1 to V2 here. And we know very well ideal gas equation PV equal RT. So with the help of this equation, so where we can write P equal to, this can also be equal to K or RT. So where P equal to RT by V. Understand? So assume this is equation number 1 and this is what equation number 2. And substitute 2 in 1, substitute 2 in 1. What we get there, if you substitute, then we get W equal to integral V1 to V2, integral V1 to V2, there we get 1 by V, so here it is RT dV. So what T here? What is the temperature? Temperature is the constant through this line, so that the temperature is how much there, that is what T1. Understand? So we'll write this one as W equal RT1 integral V1 to V2, right? So 1 by V dV. So integrating this thing will get W equal to, already you know that integral 1 by V is nothing but log V, and substitute V1, V2 values, then we'll get your RT1 natural logarithm ln V2 by V1. So this is what equation number 3, the work done during the isothermal expansion. So W, here we can assume this can be considered as W1, and W1 equal to RT1 ln V2 by V1. The work done by the system is this one. The work done by the system is equal to the heat energy received from the source. How much heat energy is received from the source? We can consider this one as W1 equal to Q1, that equal to R, here it is T1, and ln V2 by V1. So let us assume this is what equation number 3. So this is the process, that is what isothermal expansion. Now let us see what is adiabatic expansion. What is happening in the adiabatic expansion? If you observe carefully here, at point B, pressure of the system or working substance is how much? P2, V2, T1. And in this process, in the adiabatic expansion line, see there its pressure and volume, and also as well temperature also changing, where the temperature is changing from T1 to T2. So let us see how much work is done during the adiabatic expansion. You have to remember this equation. Right. Now the second step is adiabatic expansion. See, here what I am doing, I'm going to place the working substance on the insulating stand. I'm going to remove the working substance from source and placing on the insulating stand. So at the time what happened, still the system is, still the working substance is allowed to expand adiabatically. So what happened in that case, there is no source, that is completely insulating stand. Now the working substance is allowed to expand adiabatically. You know that what happened during the adiabatic process, right? During the adiabatic process, there is no heat exchange between the system and the surroundings, right? You know very well, right? So in that case, when the gas is expanded adiabatically, its temperature again come down. There is no compensation of temperature. Its temperature is come down until the temperature is equal to the room temperature. So let us find out how much work is done during this adiabatic expansion, right? So we know that in the adiabatic process, we write PV power gamma equal to constant. So now the work done during this process in the adiabatic expansion curve, here also let us assume there is no marginal change in pressure. So okay, so let us take work done, W equal to integral, here we can take PdV, right, integral PdV. Now the volume is changing from V2 to V3, then you have to write V2 to V3 here, and you have to substitute P value from this one. P value can be written as W equal to V2 to V3, and P value can be written as 1 by V to the power of gamma into K and dV. Let us K write outside because it is constant term. So write outside and K into integral V2 to V3 and 1 by V to the power of gamma into dV. Right. So integrate that function, then we'll get that W equal to K into V to the power of minus gamma. We'll just bring upwards, and integrating this one we'll get minus gamma plus 1 by minus gamma plus 1, and the limits goes to V2 to V3, right? So substituting the limits, we'll get there K by 1 minus gamma into, so where we have to substitute V3 and V2, so we'll write V3 minus gamma plus 1 minus V2 minus gamma plus 1. Understand? Now from this equation, we'll get 1 by 1 minus gamma into K. Here we'll write V3 to the power of minus gamma into V3. This can also be written as minus K into V2 to the power of minus gamma into V2. Right? Alright. So how can we write KV3 to the power of minus gamma? So if you send this one to the right side, we'll get P, but P2 equal to K into V3 power minus gamma. Like that. So here we'll get W equal to 1 by 1 minus gamma into, we'll write here P3 V3 minus P2 V2. Understand? So here we know that PV equal to RT. Substitute PV equal to RT value here. V3 P3, at this time the temperature at point C can be T2. So here we'll get RT2. So W equal to 1 by 1 minus gamma into RT2 minus RT1. Take R common and we'll get finally, if you take R common, so we'll get finally W equal to 1 by 1 minus gamma into, take R common and T2 minus T1. But we know that, here we know that T1 is greater than T2. T1 is greater than T2. Then you have to write here, take here R by, instead of writing 1 minus gamma, you have to write there gamma minus 1 into T1 minus T2. So this is what equation number 4. Equation number 4. So this is represented W2. The work done during the adiabatic expansion is how much? W2 equal to R by gamma minus 1 into T1 minus T2. Understand? Assume this is what equation number 4. Now, let us move to the next stage. That is what the direction C to D. We have completed two paths. One path A to B, another path B to C. This is isothermal expansion. This is what adiabatic expansion. Now we have to move another step, that is what isothermal compression. So what we can do in isothermal compression, let us see here. So during this isothermal compression, we can remove the working substance from insulating stand, and let us place that working substance on the sink. Let us apply externally. Let us do the isothermal compression. So that means what happening here, the force is, the work is done by the surroundings and the system, right? So when it is compressed isothermally, what happened here, and what I'm doing here, I'm placing the work substance on the sink. Its temperature is equal to the temperature of the surroundings. Now it is allowed to compress isothermally. So what happened during the isothermal compression? During the isothermal compression, here some heat, that means its temperature of the gas is slightly raised. Now what happened? Temperature of the system is slightly raised. To compensate, to make the temperature is invariable, now the system will give some amount of heat energy to the surroundings to make the temperature is constant, because it is a isothermal compression. There is the heat transfer takes place from the systems to the surroundings. The work is done on the system. In isothermal expansion, work is done by the system. In isothermal compression, work is done on the system. Now the heat energy is given to the surroundings. Let us see how much work we are going to done in this process. Isothermal compression. This is what third stage. Isothermal compression. Isothermal compression. Right? So what happened here? So the work done can be taken as W equal to integral P dV, you know very well, right? So here the path represents C to D, where the value changing from V3 to V4, understand? So substitute P value, we know that PV equal to RT, and substitute this value, we'll get there. But the temperature, you know that the temperature at point C and point D is how much? T2, right? So temperature is T2, so let us write here RT2 by, here I'm writing V and dV, where the value changing from V3 to V4. Understand? So from this equation, so you know very well that what we get RT2 ln, so we get V4 by V3. Just like isothermal expansion, RT2 ln V4 by V3. But here, work is done on the system. That is why here the work can be represented W3. Here we can write this one as W3 equal to minus RT2 ln V3 by V4. Remember this function. Understand? W3 equal to minus RT2 ln V3 by V4. This is equal to Q2. See, the work done during the isothermal compression is equal to the amount of heat given to the surroundings. The amount of heat given to the surroundings, then that can be W3 equal to minus RT2 ln V3 by V4. That is equal to the Q2, right? So just remember, assume this is what equation number 5. Equation number 5. Alright. So now the last step is what here? Adiabatic compression. Right? Adiabatic compression. That is the fourth step, final step. So let us see what we are doing in adiabatic compression. What we are going to do. Here we have to remove the working substance from the string and place it again on the insulator. Now let it allow adiabatic compression. What happened during the adiabatic compression? During the adiabatic compression, the temperature of the substance is slightly raised. Now there is no heat transfer between the system and surroundings. You know that is what obviously adiabatic process. So let us find out how much work is done during this adiabatic compression. Right. fourth one, adiabatic compression. Diabatic compression. Right? So this line represents adiabatic compression. Understand? This line represents adiabatic compression. Now the work done can be taken as W4, that equal to integral PdV, with the value changing from V4 to V1. Throughout the system, we assume that the pressure is constant. Understand? Now, so this can be V4 to V1, sorry, and we know that PV to the power of gamma equal constant. Substitute that value, then finally we'll get the W4 equal to, right, so write K outside and integral V4 to V1, and if you substitute the value 1 by V to the power of gamma dV, and that equal to K into integral V4 to V1, and this can also be written as V to the power of minus gamma into dV, and after integrating this one we'll get there K into V to the power of minus gamma plus 1 by minus gamma plus 1. Understand? And substitute here V1 and V4 values, see what we get there. W4 equal to, right, W4 equal, so we'll get there K into, so V1 to the power of minus gamma plus 1 minus V4 to the power of minus gamma plus 1 by 1 minus gamma, right, by 1 minus gamma. So just doing little bit adjustments, what we get there K into, so V1 to the power of minus gamma into V1, and minus here K into V4 to the power of minus gamma into V4, and we'll write 1 minus gamma. So substitute here with the help of this equation. So we'll write P1 V1 to the power of gamma equal to K, and P1 is equal to K into V1 to the power of minus gamma. Substitute in this equation, then we'll get W4 equal to, so we'll get P1 V1 minus, here it should be P2 V2, so V4, here it is what, P4, okay, so write by 1 minus gamma. So we know that PV equal to RT. With the help of that equation, we'll write this one as RT1 minus RT4. RT4 is nothing but, here we'll write at point D, the temperature can be what? We know that T2 by 1 minus gamma. So right, so alright, so from this equation W4 equal to, so R into, so where we write T1 minus T2 by, so 1 minus gamma. So understand, this is what equation number 6. So we got 4 important equations. One is equation number 3, equation number 4, and equation number 5, and this is what final equation, equation number 6. This is work done during the adiabatic compression. Now we have to see total work done during this process, right? Now the total work done during this process can be, so it can be W equal to W1 plus W2 plus W3 plus W4. Alright, so here if you observe carefully, W2 and W4 both are equal, and the direction is negative. See there, if you see equation number 4 and equation number 3, they cancel each other. So let us cancel these two things, and finally we have only W equal to W1 plus W3. Understand? Here we know that very well. During the isothermal compression, work is done on the system. So that is why instead of taking here W3 positive, here we can write W3, W equal to W1 minus W3. Understand? So we know that what is W1 is equal to the heat energy taken from the source, that is equal to Q1, where W3 is equal to Q2. So this is absolutely equal to Q1 minus Q2. So total work done during this entire Carnot cycle is how much? W equal to W1 minus W3, or that equal to Q1 minus Q2. So this is the work done. So again we have to substitute W1 and W3 values. Let us write W1 is equal to, we know very well that is RT1 ln, what is that, V2 by V1, and minus R, here it is T2, so here we get ln and V3 by V4. Understand here two things. So let us go through the line adiabatic expansion. So in this adiabatic expansion line, so we know that one formula, PV power gamma equal to, can also be written as, with the help of ideal gas equation. So we'll write here T V to the power of gamma minus 1 equal to constant, right? So let us apply this formula at point B and point C. Let us equate the things, then what we get there. On this adiabatic expansion curve, here we'll write, this can be, here it is T1 and here it is V2 to the power of gamma minus 1, that equal to, here we'll write T2 into V3 to the power of gamma minus 1, right? So from this 2 points we'll get T1 by T2 equal to, where we get there V3 by V2 to the power of gamma minus 1, understand? And now same thing can be taken at point D and point A, that is what adiabatic compression line. So on the adiabatic compression line, let us apply this curve, this formula, there we'll get there T2 V4 to the power of gamma minus 1 equal to, here we'll get there T1 V2, T1 V1 power gamma minus 1. Right, so from this equation we'll get there T1 by T2, so equal to, T1 by T2 equal to V4 by V1 to the power of gamma minus 1. Understand? So let us assume, so this is what equation number 7, understand? Equation number 7, so here it is number 8 and this is what number 9. Okay, so from equation number 8 and 9, from equation number 8 and 9, so what we get there, with the help of equation number 8 and 9, we get there, here it is V3 by V4, V3 by V4 equal to V2 by V1, right? So using this one, let us assume this is equation number 10, substitute equation number 10 in equation number 7, so what we get finally, so we'll get finally here, substitute equation number 10 in equation number 7, we'll get that the net work done can be W equal to RT1 ln V2 by V1 minus RT2 ln V2 by V1. Take ln V2 by V1 common, then we'll get there R, here it is ln V2 by V1 into T1 minus T2. So this is the net work done during this Carnot cycle. So right, so this is our required equation. This is our required equation. Now, so we are going to find out the efficiency of this Carnot engine. So we know that how can we write efficiency? This efficiency can be written as neta is equal to efficiency can be neta equal to net work done by the amount of heat given to the system. So with the help of this formula, then we'll write neta equal to, that is what, W1 minus W3 by, here amount of heat given to the system can be Q1. This can also be written as Q1 minus Q2 by Q1, right? So from this equation, so we know that let us substitute Q1 minus Q2 and from this equation we'll get there neta equal to 1 minus Q2 by Q1, and if you substitute the Q2 and Q1 values, so otherwise the net work done, it can also be written as, that is equal to, here R ln V2 by V1 into T1 minus T2 by, so where it is Q1 value is how much, R ln V2 by V1 into, here it is what, T1. So let us cancel these things and finally we get neta is equal to 1 minus T2 by T1. So this is what efficiency in terms of heat energy, here the efficiency in terms of temperatures, right? So this is the whole thing about Carnot's engine, the work done and the efficiency, so we have derived, right? Okay.